manage to, I guess, just put it away and then do it over the weekend. I'm going to unsubmit it anyways because the last 5 or 6 questions are more for the next DYU anyways. And there was a big struggle on those. Okay, we're going to talk about conditional probability and independence rule. And we have to do that quickly because Mr. Anderson's going to be applying it in his lesson after lunch. And then we're going to do the DYU and answer some questions. So we'll do this after lunch. No, not after lunch, probably Monday. Okay, so this is all about independence and calculating probability of 2 or more events when the events are independent. And so that's building into the idea of dependent events, etc. So, alright, this was the first page of day 2 yesterday. And so I went ahead and just kind of wrote this up here. So based on the data that we had, we found out that the probability of getting taco tongue, given you can do evil eyebrows, was not the same as the probability of taco tongue, given that you cannot do evil eyebrows. And so I want to talk about 2 things. So first, Charlie, you mentioned yesterday, wouldn't it be better to have decimals? And if I'm trying to compare 2 probabilities, it's definitely easier to compare the decimals. Okay? If you are worried about the probability because you can't really picture what's happening, which I think is what Charlie said yesterday, then it might be better to get the decimals so that you can see where it is between 0 and 1. Okay? So just looking at the fraction doesn't tell you a lot? Yeah, sure. Now, the thing that Madeline, you brought up yesterday was, they're pretty close, right? And so on the AP exam, because I checked into this, I did some research, on the AP exam, the probabilities will be identical if they're independent events. But in the real world, it's not very likely that the probabilities are ever going to be exactly the same. And so in statistics, you can do an inferential procedure to see how different are they to make me think if they're independent or not. And so there's a way to measure the difference based on like the sample size and things like that. And so there is a way in the real world to determine independence even if they're not identical. Because yeah, it's very rare that they'll be identical in the real world. Does that make a little bit of sense? Okay. But on the AP exam, if they're independent, those probabilities will be the same. Kenzie?
I thought me and Sophie both have no on our paper because I thought...
Oh, that is supposed to be a no. That is me writing wrong.
Oh, okay.
Yeah, sorry. That was supposed to be a no. Definitely. All right, backside. I think what I read, and obviously what it's not said, is are they dependent? So I said yes, but yeah, they're not independent. Okay, then we did this part yesterday. You'll notice I even updated it with the correct numbers. I think, because I remember this, I think I made it out of 300 to mirror Hillcrest High School better last year. And then, whatever. Anyways, we went through these probabilities. The probability of being able to do taco tongue from this data at that high school was 0.8. The probability of being able to do taco tongue given you can do evil eyebrows was 0.9. And then the probability of being able to do taco tongue given you can't do evil eyebrows was 0.75. So were those independent events? No. And that's where we ended yesterday. The answer is no, because those probabilities are what? They're not the same. They're not equal. Okay? So I'm starting this here. Suppose that the ability to taco tongue and evil eyebrow are actually independent events. Determine the following probabilities. So not based on that table given, I want you to talk to your group for just 1 minute. What do you think these probabilities will be if taco tongue and evil eyebrow are independent events? So talk with each other. Try to figure out what you think those probabilities might be. You might want to get in this report. Yes.
That is not
You'll survive.
Yeah, just if they actually are independent. So don't worry about the table. Just think about if they were independent.
If they are actually independent, what are those probabilities?
Just like a yes or no question.
No, we're supposed to think about what the probability would be.
Did you get a haircut? Yes, I did.
Probably start telling people no.
I know. I thought about just trolling people. Yeah, I was like, oh, it's been this way my entire life.
Yeah, but we're not worried about this, because this is saying if they're.
So what do y'all think of the
So this
probability?
is, we said they're not independent, so we're just worrying about like unavailability.
For number 5?
Because everybody can do it.
Yes.
Isn't it the value?
Suppose that the events are actually independent. We already know the probability of taco tongue is 0.8, so what are the rest of these probabilities?
Okay, right, because if, so if you know that someone has evil eyebrows, but they're independent, does that actually change
What do we think?
the probability of someone being able to do taco tongue? No, right? If
Well,
they're
if they're
independent, the probability
Does it
doesn't
matter
depend
if
on
you
what
can
happens
do evil
first.
eyebrows? Okay, so what would that probability be if it does not matter that you can do, whether you can or cannot do evil eyebrows?
I'm sure I know what I'm talking about.
Is that what your group agreed to? Yes?
Well, what value do we have?
Okay.
Wait, ain't.
And we just said it should
Alright, so let's talk about it.
be the same, right? So it should be,
So, if they're actually independent events, so eyes and ears here, if they're actually independent events, does it matter if you can do evil eyebrows or not? No?
No.
So then what would be the probability of yes, taco tongue, given that you can do evil eyebrows? It'd be 0.8. What would be the probability that you can do taco tongue, given you can't do evil eyebrows? It would also be 0.8. It doesn't matter if you can do taco tongue or not, that probability would still be 0.8. Okay? So remember, the whole reason we said earlier that they were not independent is because those probabilities were not the same. They're independent, so those probabilities are the same. Okay, so fill in the table based on these probabilities, right? So remember, the probability that you can do taco tongue, given you can do evil eyebrows, is 0.8. So, of these 200 who can do evil eyebrows, what's the probability that they can do taco tongue as well? 80% or 0.8, right? Think about that. Use that information to fill in that table. 1 minute, and we can come back and talk about it.
Aren't we just really at the same numbers or?
Now remember, we're basing it on them being independent events now. Given. It's a conditional. That's how we write conditional probabilities. Remember, that's all in that formula sheet.
That came from up here. He's saying 180 out of.
What do you think 180? Wouldn't that be 90% of the evil eyebrow people?
It's 80%.
Or what does it say? What proportion
Isn't that what that one is?
of the
Given
evil
yes,
eyebrows can do
eyebrow,
taco tongue? 60. Remember, what this is saying is 80% of my evil eyebrow people can do taco tongue. The probability that you can now, for which one? 40. Yes.
Well, what's our condition? Which one are we given?
Probabilities.
What is the bar? So the bar means given, right? So it's taco tongue given evil eyebrow.
So the probability is 0.8.
Exactly.
Yeah.
Okay, but 0.8 of what?
means that
Okay,
80%
that's
of
what I'm
evil
asking,
eyebrow.
like,
Well, how many evil eyebrow? So remember,
how do
this
you do
is,
that?
but this is the condition of
80%
evil eyebrows, okay? So do I care, right, looking at this probability, do I care about no evil eyebrow?
Because it's yes, taco tongue given,
No.
yes, evil eyebrow.
So that is saying that 80% of the
But then
evil
we gotta look at
eyebrow
values.
can do
So
what?
we said our condition is yes, evil eyebrow.
Okay, so what's 80%
So
of
what's our
the
condition?
evil eyebrow?
200 students, right?
How do you determine what
There you go.
But I know my
That's 80% of 200. What?
I know these are here.
Oh, well, that's what I was just saying before, because we identified that the condition was evil eyebrow, so we're looking.
How'd I get
at
80%?
Yeah, how do you do that?
0.8. Remember, what did we say these events are? Okay, remember, over here, we talked about the fact that if they're independent, knowing whether or not one event has occurred does not change the probability that the other will occur. Well, if it doesn't matter if they can do evil eyebrow,
So we're just saying, but because we got 0.8 for that, we're just saying these can both do more.
if they're actually
Sure, you
independent
gotta lock
events.
in.
So remember, the whole assumption now is that they are independent. If they are independent, does this condition matter? Okay, so then probability of taco tongue was 0.8. So if that doesn't matter, it's still 0.8. If that doesn't matter, probability is still 0.8. What?
I got it, but I didn't get it.
Okay.
I get it.
All right. So guys, real quick reminder.
That's okay.
We are saying that these here are what kind of events?
Independent.
Independent, okay? The whole idea of independence is that the condition, this condition does not matter whatsoever. So if the probability of taco tongue is 0.8, whether or not they can do evil eyebrows, the probability of taco's tongue is still 0.8, right? Like the idea is that this condition doesn't matter if they're independent. So independent. So if independent, the condition doesn't change anything. We need to recognize that. That's why it's 0.8 all the way across. And so we're saying of the evil eyebrow, how many can do taco tongue, or what proportion can do taco tongue? 80%. 80% of 200? 160. Which leaves us with 40 here. Okay? Probability of taco tongue, given you can't do evil eyebrows, is still 0.8. So of the no evil eyebrows, what proportion can do taco tongue?
30-20.
Well, 320, but the proportion would be 80% and 80. Okay? Yes, Madeline.
Do you remember when you wrote the fraction divided by the fraction yesterday? For, like,
Yes.
given? I'm trying to like make that make sense with those two, but I can't visualize.
Okay, so probability of taco tongue, given you cannot do evil eyebrows. Now looking at that table, so remember that's the probability of taco tongue and no evil eyebrows divided by the probability of no evil eyebrows. That would equal, so the probability would be 160 out of 600. No, 320 out of 600, sorry. So there's 320 that can do taco tongue and can't do evil eyebrows out of all 600 people. Divided by the probability that you cannot do evil eyebrows is 400 out of 600. But remember I told you I would not ever do the fraction divided by the fraction if I have that table, because to divide by that fraction I'm going to multiply by the reciprocal. And so notice, I'm just left with the intersection divided by the condition. Okay? So you can, the reason why you need this is if you're not given a table. If you're given a table though, you can just pull it straight from there. Okay, so 320 out of 400. Notice that is now that 0.8. Okay? Alright. So the question is, how can you tell from a two-way table if two events are independent? Charlie?
If the probability of A given B is equal to the probability of A given not B.
Okay, so the probability of A, given that B is true, would equal the probability of A given B is not true, and that could actually equal one other thing.
A minus
Probability
of A.
At the probability of
That'd
A.
be the probability of A, because remember, did that condition matter? No. So how do we check independence? This is how. We check those probabilities. And so what I would point out is, it's proportional. A, the marginal relative frequency, compared it to the conditional relative frequencies. So notice, the marginal relative frequencies equals the conditional relative frequencies, because that condition did not matter. So notice that marginal relative frequency, 480 out of 600, that's 0.8. That equals 320 out of 400. That conditional relative frequency of only no evil eyebrows is equal to 160 out of 200 with a condition of yes evil eyebrows. So if they are independent, this probability holds true. In the real world, how often does this probability hold true? Almost never. But on the AP exam, if they are independent events, this will hold true. So, if you're ever asked about independence, this is how you check independence on AP exam. and how to check independence on the AP exam. Okay. So just a second, for y'all to be able to get those notes down.
So Mr. Kenny,
Yes, ma'am?
calculating given that if yes type of form that is not equalized, that you calculated with fractions, can I just say if there's a data table 160 over 200, because we can just do that and put the same value?
I mean, you just look at the intersection divided by the total for that condition, right? So you would just look at the counts, right? The counts of the intersection divided by the counts for that condition. All right. Looks like we're ready for those quick notes. Okay, conditional probability. What should we write down? Like, what is a conditional probability? Yes, it can, like that, but when we say conditional probability, this is the probability of an event happening. And then y'all started to say a really important word, given that another is already what? Yeah, that's actually a great way to say that. The probability that someone can do taco tongue given that they can do evil eyebrows. I'm not looking at anybody else, I'm only looking at the people that evil eyebrows is true for. So the probability of an event happening given that another, so let's say B, is already true. Good. And so we saw this on the formula sheet. I think I showed it to you on the formula sheet, right? This equation?
Yeah.
So this is on your formula sheet. Probability of A given B. How would we calculate it? Probability of A plus and. Remember, probability of A and B.
Divided by probability of B.
So remember, B has to be true, right? So I don't care about everything in A. I only care about the A that intersects with B, right? That's a joint probability right there divided by a marginal probability, right? So it's the probability of their intersection divided by the probability of B. And you talk about the general multiplication rule within yours, right? Do you talk about how to calculate this if they're independent in your lesson?
Yeah, it's like the second question
Okay.
gives them a way of doing it.
Okay.
And then they find the way of doing it if they're doing it.
Because I was going to talk about it right here, but it already shows up there.
Yeah, on question 2 it specifically says like you can use, and it tells them what to.
Oh, so it just goes and tells them. I'm going to talk about
Yeah,
it.
so you.
Yeah, yeah, yeah. Okay, independence. We have independent events if knowing a condition, so we'll treat B as that condition. If knowing a condition, what?
Predicts A.
If they're independent,
Doesn't.
it doesn't affect. Probability of A. Right, so if knowing a condition doesn't affect the probability of A. So probability of A given that B happens, probability that of A given that B doesn't happen, and the probability of just A happening are all what? Equal or the same, yeah. Okay. So last thing we're going to talk about with this is, if we have two independent events. What is this? What is another way to write this if we have independent events?
Is not equal.
So just rewrite this. Think about this down here. How can I rewrite this statement if we have independent events?
Probability of A.
Okay, just write it as probability of A, right?
Yep.
So if independent, then the probability of A is equal to probability of A and B divided by probability of B. So if we have independent events, how could I calculate the probability of A and B? Think about this right here that I got us to.
The probability of A multiplied by the probability of B.
And y'all have done this before if you've ever done probability, right? So if I roll 2 dice, what is the probability of getting an even number on one die and a multiple of 3 on the other die? Well, do the 2 dice affect each other? Not really. So what's the probability of getting an even number on one of the die? Just any even. So 1/2. What's the probability of getting a multiple of 3? Multiple of 3? 1/3, right? 2 out of 6. And wouldn't you just multiply those two probabilities together? Most probability that you've ever done up to this point is independent events. And so that should seem really straightforward. I just want to make sure we understand where this is coming from. So when's the only time you can use this equation? When A and B are independent. If you know A and B are independent, probability of their intersection is just probability of A times probability of B. Okay? I'm going to quickly go through a couple of quick progress check questions. But we got to do this quick because I did make the DYU short, but not that short. And Mr. Anderson's got to teach after lunch. So, out of the 6 people who did this progress check, only 1 person got this one. Okay? Guys, the question simply asks, right here, based on the histogram, what is the probability that at least 4 of the next flights at the airline will be overbooked? Here's 4, and here's 5. But notice it says at least 4. We gotta be careful with our at least, our more than, because that's what I think a lot of us did, is we only looked at the 5, okay? Guys, if it's at least 4 of the next 5, just add those together, okay? So right here, really quickly, I'm going over this because you need this. A certain population of birds, about 40% of the birds have a wingspan greater than 10 inches. We're doing a simulation. And we're looking at this probability of 1 bird in a sample of 6 birds with a wingspan greater than 10 inches. And we're going to assign digits 0 to 9 to model the population. Well, I think what a lot of people got thrown off by was the 1 bird in 6. However, what percent of birds have a wingspan greater than 10 inches?
40%.
40%. So if I'm looking at the digits, of those 10 digits, how many?
0 through 3.
0 through 3, or at least any combination of 4. So when we look at this and we're saying, hey, 40%, like this is true. Remember when we said 1 in 6 wins, we let one number out of the 6 be a win, right? Here, 40% is what we're assuming to be true, so 4 out of the 10. So yeah, 0 to 3 represents wingspans greater than 10 inches. Okay? Oh, right here. A lot of us picked E right here. Can we ever do probability in the short run?
No, that's long.
It's in the long run only, guys. When we talk about probability, we interpret in the long run. 0.6 represents the probability in the long run for many internet users. when you talk about probability and you interpret probability, you've always got to talk about it in the long run. And you got to know how to interpret probability. Quick last detail, because this came from yesterday, and then we're going to start that DYU. This will not hurt you on the DYU, but we got to recognize this. Sometimes writing things out using our notation can be helpful. Probability of brown eyes equals 0.35. The probability of brown hair is equal to 0.45. Then we are told 60% have brown hair or brown eyes. So probability of brown eyes or brown hair is equal to 0.6. And then it asks us, are E and H mutually exclusive? Well, if they were mutually exclusive, that'd be probability of E and H would equal what?
0.
Do we have a formula that connects the probability of two different events, the union and the intersection?
Yes.
Probably.
Probably.
Plus, E.
Probability of A or B equals,
Probability of A plus probability of B minus probability of A and B.
and we have that formula sheet, but when you are given different probabilities and you see a union, you see an intersection, and you see that, you need to think about the general addition rule. When I'm given an intersection and a conditional probability, I immediately think about that conditional probability formula. But notice here, so 0.6 is equal to 0.35 plus 0.45 minus the probability of their intersection. So, I mean, that's 0.8, right? So is that 0? No. What does that have to be to make this equation true? It has to be 0.2. That's why it was D, the probability of the intersection was 0.2. So we need to recognize, like, when we see these different probabilities, write out your probability using probability notation, and then see a way to combine them. Yes,
What was
Ian?
the difference between mutually exclusive and independent of that?
So remember, mutually exclusive means the intersection is 0. Independent means probability of A given B, the condition doesn't matter. Mutually exclusive has nothing to do with conditional statements.
Oh, okay.
Does that make sense? Okay, formula sheet out. I'm going to do something with the DYU to hopefully make it tenable. We'll see. Okay. The true false are really, there's only 4 of them, but skip the true false for now. Just do the multiple choice and the free response. Make sure you get to the multiple choice and the free response. Mr. Anderson, did you already give?
No, but I have 2 of them in mind.
And then, okay, so please try to get to the false statements, but they are pretty short questions. So you can give me the prayer model after this. Do your DYU now.
No.
Just leave it slightly cracked so that it can come back.
Okay. Hi, Star. So, we're going to start the last activity before of probability. So, this is your proficiency scale. Most of it, obviously, you guys have covered in the previous activities. We're looking specifically with this one at independent events and calculating an intersection, as well as what we have.
Keep going.
Oh.
There it is.
So this is mainly what we're doing, tree diagrams. It's the matching Starburst 2 activity. If you guys, it should be in your packet. We're going to be playing the Starburst game again, but it's going to be a little different. So we're looking at tree diagrams and the general multiplication rule, similar to the multiplication rule that we did before, but mainly this time looking at conditional probabilities and dependent events, as opposed to independent events, which is what we were looking at with those tables before. So, if you guys have this out, the matching Starburst 2, these first 2 questions are related to when we played it previously and pretty related to what we were doing before, so these should be pretty quick. So when we played the game before, we would pull a Starburst out of here, right? And then we'd put it back and we'd take another one out, right? So when we pull a first one being red, and then if I pull another one out and that's red, are those dependent or independent events? What do you say right now?
If you're not putting it back inside.
Well, when we played it previously. So when we played it on Wednesday, we were putting it back. So that would be independent, right? So this would be independent. So how can I explain that they would be independent. So how did we define independent before lunch? What did we say? So when we pulled, so after we pulled a red one, did the probability of the second one being red change? No, right? The sample stays the same and the probability stays the same. So the second one being red is not affected, right? That's what we said. Is not affected. Because we put it back and we shuffled it. It was basically like doing it the same thing just a second time. So is that clear?
Yes.
So, now this is kind of like what we were doing at the very end before lunch. So we're going to we calculated the probability again, but we're just going to write it down because we're going to need to refer to this later after we play the game again. So what was the probability that the first starburst was red when we played the game on Wednesday?
4 out of 6.
Yeah, you said 2/3, right? It's the same thing.
Oh.
Right, so there were 4 red ones out of 6. And then we said they were independent, so what does that mean the probability was for the second one here?
4 out of 6.
Also 4 out of 6, right? So this gave us a total of what?
1636.
Right. And then, obviously we were using pink ones, it's pink ones again today. But what would it look like for the pink ones?
26.
Yeah. And then they were independent, so what is the
2/6.
2/6 again? So this was
12 out of 36.
wait,
Oh,
4 out of 36. So what was our total probability of winning? What do you say, guys? 20, right? Out of, right? Remember, there were 20 different times we could win, divided by 36 total different combinations when playing the game. This was the same as 5 out of 9 divided by 9. We said that was about 55%. Right? So we're going to refer back to this when we play the game again, except when we play it now it's going to be different because, kind of like what you were trying to get to before, Raina, this time when we play, after the first one we're not going to put it back. So if I'm going to play it real quick just to show you, but it should make sense. So if I pull one out, and the way to win is the same, so I pull a red one, but I'm not going to put it back. I'm just going to shake it up again and pull another one. So I pulled a pink one, so I lost, but that's how we're going to play it now. And we're going to do it 10 times again, but I wanted you guys to think before we play this, do you guys think the probability is going to change of us winning?
Yes.
Okay, so you all say yes. Do you guys think the probability would go up or would it go down?
Down.
So, well, who thinks it would go up? Star, you said up. Does anyone else think it would go up? Star, why do you think it would go up?
Because you're removing one of the
Well, the outcomes, right? So you're removing. So you think removing an outcome is going to increase the probability of us winning?
Yeah.
So everyone else said decrease. So who thought it would be decreasing? Phoebe, what do you think?
I think it depends on which one you pull because if three out of five, like if you pull the red one, then the probability of getting another red one would be 3 out of 5.
Okay.
And your one is less than 4 out of 6, I think. Was it?
Mm-hmm. Yeah, because 4 out of 6 is like 2/3, 66, and 3 out of 5 is 60.
Yeah.
So we're going to get to that in a second. That's basically what we're thinking about when we do this. But we can think about both things, right? So basically, Star thought that removing an outcome would increase the probability. Phoebe, you're saying that the same variable is actually going to decrease the probability. So we're basically going to be thinking about those two things while we play again. And we're just going to record the results of 10 tries like last time. And we're actually going to see if it is going to increase or decrease. This is y'all's back. So 6, y'all are done?
No.
That was count, but you don't get it.
You would.
Have you put out 2?
We had
3? It's okay.
We lost.
We have lost.
Ew!
9, is that your last? How many games do y'all have left?
One more.
Got it.
We got 6.
Wow.
That's like
Oh, so
Y'all
did
cheated.
we.
Y'all cheated.
We have to count
Or
it.
it's a skill issue.
Okay, so what does it look like happened to the
It
probability?
went down.
It probably went down, right? So what is, based on the results, so what is the probability that our class won the new version of the game?
9, 13,
16, 23,
22 out of
We have a calculator,
23
guys.
out of 50. I think.
That's
22.
30.
Did the copier come to the office for a moment?
Yes.
Yep.
What is it, 22? It should be 22, right?
I'm
checking out.
So the probability for our class to
Okay.
win the new game is 22 over 50, 22 divided by 50, right? Which is 44%, right? What was the probability that we just calculated before for us winning
55.
55, right? So our probability, our experimental probability, right, based on our simulations, clearly went down, right, from the first version of the game, right?
See.
So we're going to use this version, and we're going to complete a tree diagram, which is what we're doing, to find actually what the actual probability is. So I'll keep ours up here. So ours was 44%, right?
Yes.
So 22 divided by 50. So we're going to see what this looks like based on our diagram, which should be next, right? So we're going to use this diagram to help us find what the theoretical probability is for anyone to do this game and come up with a win, right? So if we start here, what is the probability just of me pulling a red for the first one? 4 divided by 6, right? Remember, 4 times 4 red starbursts divided by the total amount of starbursts, which is 6, right? But after I pull a red starburst, what is going to be the probability that I pull a second red starburst? So, see, this is, so, Dara, you said 3 over 5, right? 3 divided by 5. Kenzie, you said 3 divided by 6, right? Is that what you said?
Can we go over how many reds and pink there is?
So, well, okay, so if I pull out a red starburst, right, I'm not going to put it back, right? So how many red starbursts are going to be in my bag now?
5. Well, we don't
Well,
know.
how many red starbursts?
3.
So there's going to be 3 red starbursts, right? And how many total starbursts are going to be in there?
5.
So what do you think the probability should be?
3 out of 5.
3 divided by 5, right? That's what I heard you say. I'm sure other people thought that too. Or some people would have thought 4 out of 6, but obviously they're not independent, right? If it was independent, like we had before, the tree diagram would have been easier because it would have been 4 divided by 6. Obviously our probability is changing. But now we want to compute our probability of the first one being red and the second one being red. So before, when we were looking at them being independent, what did we do to find the joint probability? We multiplied, right? So what do you think we're going to do here? We're going to multiply again, right? So this is 4 divided by 6 times 3 divided by 5, which is 12 divided by 30. So here our probability of pulling 2 red starbursts is 12 out of 30, 12 divided by 30. But remember when we played before, it was actually 16 divided by 36, which this is probably lower. So that's contributing to our probability going down as well.
Yeah, 0.4.
Right. So our probability of winning with 2 reds is going down once we pull out a red starburst compared to our probability of winning when we leave it in. So you guys have the tree diagrams on your sheets there. I was going to give you like a few minutes to work in your groups to fill out the rest, and then we're going to fill it out on the board. And you guys could work on the whiteboards as well. But I know the tree diagram's like drawn out on there, but if you want to draw it out on the boards too, that would work as well. But take like 3, 4, 5 minutes just to finish basically everything else that's on the tree diagram.
Yeah. And the other one,
Sure, yeah. If you want to start, that's fine.
Yeah.
Yeah, so you're not working alone? Cool.
Also get a couple just in case and then
For the second or third box?
Okay, so
That's
Two like middle ones? Yeah.
after the first red, probability of
2 out of
second yellow is 2.
First is red, first is yellow.
Well,
It
it's
still has
two out
a
of
4 out of 5.
Yes.
Oh.
And if the person's only has 1 out of 5.
Right? Makes more sense now?
Yeah,
Oh, shoot, I put
for the
Six.
first yellow, and the second yellow.
Alright,
Oh,
what'd you
okay,
get?
so six.
So this is what
Cool.
you guys gotta put your, I have not, but yeah, so you even
One
wrote
would-
6, but you had crossed it out, right? Because the total
No,
number of
okay.
starburst
Yeah.
goes down, right?
I forgot about that.
Right, yeah.
We all
Is it
do a
not
tree
352?
Yeah, we're just gonna go over it and then we're gonna go over the other questions after.
5 left.
Once we have it all filled in up there, but I think most groups are done already, right?
Just the whole.
You guys got your diagram?
What is the probability that Kenny was right?
Ian, what's
It's not clicking for him.
I'm not talking to you.
It's not talking.
what is not?
It's like-
You can't have 2 3/5. That's
Cause there's only
6
two pink.
Remember, so this probability is for yellow, right? Oh, well, pink, yeah. So well, remember probability is what? What's our, how are we
Zero to
defining probability? Well, that's what it ranges between, right? So what is our definition of probability, right? If we have probability of pink,
Probably pink.
so what is the top and the bottom? Gonna
Oh, it's
Well, when we did it for red, when we did it for our red, right? For the second one to be red, we said 3 divided by 5, right? Where did the 3 come from here?
because that's how many like
That's how many what we get?
red.
Red, right? And where did the 5 come from? Okay, so then if we go to, so this is based on, right, if we follow our tree, after the first one's red, right? After the first one's red, what are we trying to find? The second one being pink, right? So what should I put on top? 2, why?
Because that's the number observed.
It's the number of pink ones, right? And then what should I put on the bottom?
The total number, which is 5.
Which is 5.
Okay,
Yes, sir.
quick cue.
Yes.
Okay, so basically, this is what we do.
Well, we're gonna go over that after.
I didn't answer.
No, I didn't, don't pull it just for
Or is it 6 times 4 fifths? Go.
Well, the condition is that they want, well, what are the outcomes that they want? We're gonna go over this. But the condition isn't that, what's the condition though? The condition is given that they want, right? Yeah. So is everyone done with the tree diagram? Ian, are you finished?
Sure.
Oh.
And then you multiply. 12, 7, 8, 8. Right?
Yeah.
Oh, and always apply multiplication.
That's always our joint, so yeah, we're always.
So we multiply 8, 6, 16.
And we're gonna go over that after, and then quick notes as well, but yeah. We're always looking at multiplying.
I don't know, probably.
Dude, 3 times 2.
Where are you getting?
What do you?
Yeah, well, remember, we're following the tree, right? So we start here, and then we're going here. So it's there. So it's this one times this one gives us this one.
Okay.
So we follow our branches there. I'll probably start going over it in a second. Is everyone else done with the tree diagram so far?
Yes, we are.
Okay, cool. So let's go over it. So, still working with the first one being red. If I take the first one out and it's red, what's the probability that the second one I take is going to be pink?
2 fifths.
So 2 fifths, 2 divided by 5. We just went over that, Ian. How come it's 2 out of 5 this time?
Because the 2 is the total number of pinks that there are, because we didn't take any on the first try.
Right.
And 5 is how many that is left after the first try.
Right, exactly. So if we think about probability just in our definition of successes divided by total outcomes, when we're looking for the probability that the second one is pink, in this case our successes are how many pink ones there are, which is still 2 because we didn't take out a pink one. And then divided by, but we have to change the total number of outcomes because now there's only 5 starbursts left in the bag, not 4. So then what do we get for the probability of the first one being red and the second one being pink? So, wait, 4 out of 15 is the same if that's what y'all said anyway. Because you just
8 out of 30.
simplified it. And where did the 8 divided by 30 come from?
2 times 4.
And this
And then
roll
5
of
times 6.
Multiplication of fractions.
Which fraction?
For the 4, 6, and the 2.
4 6 and the 2.
Right.
Multiplication.
We're gonna look more into this later, but yeah, we're always multiplying this times this to get that box, right? Now we gotta work with the bottom. So what was the starting probability that the first one we pull is pink?
2
6.
2 divided by 6. And then after the pink one's pulled, what is the probability that the second one's gonna be red?
4 5.
4/5.
Okay. And what does that make our probability that the first one's pink and the second one's pink?
8 out of 30. 4 15.
I flipped mine.
Oh, I bet you knew that.
Oh.
This comes from what?
Oh my god, Dixie, please.
My necklace. Sorry.
I'm not
Welcome back.
Like a sitcom.
The laugh track?
Okay, sorry.
Okay, where does the 8 divided by 30 come
2
from?
over 6 times 4 over 5.
I could cry right now. Why do I have 4 bracelets on my hand? Oh my god. So good.
Is that 1 over 5? Or, yeah.
Mm-hmm.
It's 1 over 5.
Yeah.
And 1 over 15.
Sure, yeah, this would be,
2 30.
right, which is the same thing as you said anyway, right now, but I'm just gonna keep it out of 30, right, because I wanna think about it in our definition that we were using before, like successes divided by total outcomes, because there's 30 different ways of playing the game. So, this would be 2 divided by 6 times, in this case, 1 divided by 5, right? Dixie, do you have this sheet? You're fine. Alright, so everyone has these values filled in, right? And everyone's tree diagram looks like this, right? So now we want to use this diagram to find our theoretical probability of winning. So how can we use this diagram to discover what our probability would be? Charlie?
You add up the probability of the 2 winning outcomes being one red and 2 red, and 1 pink and 2 pink, which would be 12/30 plus 2/30.
That is exactly right. Does everyone see where Charlie got that from? Right? So the tree diagram, the reason we make the tree diagram is so it's clearly visible every single probability of each outcome for our dependent events, right? Because we don't really want to make this for independent events because these probabilities aren't going to change. So we just want a table and those probabilities visible. But here we can clearly see our different probabilities for dependent events. And then we want to count, it's very easy to see, we know that winning is when they're the same, so pink and red, and then we're just going to add them. So that's where Charlie got this 14 divided by 30. So 12 divided by 30 plus 2 divided by 30 was 14 divided by 30 as our probability of winning in this case. But does anyone remember or have the other sheet what our theoretical probability was for, oh well we actually just came up with it on this sheet, right? On question 2?
44%.
Yeah, 54, but what was that as a fraction? Oh, I guess
5 ninths.
5 ninths, right? So 5 ninths is going to be greater than this, right? And this as a percent, I'm not sure what
It's
that would be.
46 repeating.
46? So this is 46 repeating, and this is 55.5 repeating. So clearly the probability of winning the game when we played it the first time, when they were independent, is going to be greater than our probability in this case. Ian.
Can you explain again why we added 12/30s and 2/30s? Like, what were we trying to look for?
So we were looking for our theoretical probability of winning, right? So for me to win, right, I could either pull a red one and then pull another red one, right? So that's going to be this branch here. Or I could also win by pulling a pink one and then pulling another pink one, right? So then I have this probability, and then I would just add them. Because either one could happen, right? So it's this, because this could happen, or this could happen, and either way we would be winning, right? So it's just our total outcomes, and this is why I left these as fractions, because if we think about it as our successes divided by our total outcomes, so there's 30 outcomes of playing the game, right? there are two different ways of pulling two pink ones, right? I could pull the first pink one and then the second pink one, or I could pull the second pink one and then the first pink one. And then there's 12 different outcomes of winning with red. So then we would add the 12 and the 2. So that's 14 total successes divided by 30 total.
Thank you so much.
Of course. So does everyone kind of understand where we got the theoretical probability and understand that once these are dependent events, our probability of winning is going to go down, right?
Yes.
So I'm going to erase this. And we're going to refer back to it for these next questions, but... Oh, here we go. So find the theoretical probability, we just said that was what, 46%?
46 repeats.
Okay.
Yes.
What is this, 12? I'll keep these out, right?
Yes.
Yeah.
Yes.
Yeah.
Yes.
Yes. Oh, my bad.
Don't listen.
Yes.
Okay.
And compile it.
So now question 6, what is the probability that the first candy was red given that the person won the game? So if we see given, what kind of probability are we looking for here? Conditional, right? We want a conditional probability here. So we got to identify what is our condition. Is our condition that the candy's red, or is our condition that we won?
They won.
The condition's that they won, right? It's always given that they won.
Oh, so it's 14.
So our condition is given that they won. So how many winning outcomes did we just say that there were? There's 14, right? So if our total amount of winning outcomes is 14, how many of those winning outcomes are when the first candy's red? 12, right? Because our only wins are when both candies are red, which was 12, right? We thought about this before when we were dividing fractions. Another way of doing this, remember? So what does this 12 represent? Or the 12 out of 30, what did that represent?
The red's one just right.
Right. So this is the probability that the first candy was red and we won, right? So we have the first candy being red and the probability that we won, right?
How do you determine that probability from the?
So if we follow our branches, right? So the first candy being red and then the second candy being red, there's a 12 out of 30 chance. And because we know that we're winning, right? Remember, red and red is a win, right?
Yeah.
And there's no way of winning with the first one being red and the second one being pink, right? So we know that this probability would be that 12 out of 30, right? And then, so this came from, if we divide by, so the 12 out of 30 is the probability that the first one is red and we win. And what can I divide this by to get, where did that 14 come from?
The win.
It came from the total wins, right? So this is the probability that we won. So we worked with this before in that taco tongue and eyebrows thing before lunch, right? We saw this. Actually, that's what it is right here. So now I have kind of like this, right? So A and B divided by B. But this is if they're independent, right? Are our events here independent? No, right? So this formula looks similar, but it's going to be a little different, right? Because the probability that the first one was red and we won isn't the same as it was before, right? Or the second one, because in order to win, the second one needs to be red, right? But the probability of the second one being red isn't the same anymore as it was before, right? So if we have the probability that the first one, or what can I say? The probability that we win, so if the first one's red and we won, we could say the probability that we win what? We were looking at conditional probabilities, right? Well, what could I write this as, if the first one's red?
Probability of red one.
Well, if we have the probability that we won, right, this 12, or where is it? The 12 out of 30 is the probability that we won
And a red.
and a red, but what did we say?
First red.
The first one was red, so the condition was red, right? Given that the first one was red, the probability that we won. That's what's different from there, because the probability of A and B, remember, what did we say about the probability of B happening is, if it's independent, compared to the probability of B happening with a condition?
Is the
It's the same.
They're the same, right? If it's independent, these two are gonna be the same. But in our game, are these two the same anymore? No, right? We're gonna look at that in a second. So, and then there's,
Is it red given win or is it win given red?
so the probability that we won, given the first one was red, is the 12 out of 30.
Okay.
Because the probability, because the condition
Oh,
is that the first one's red, which follows this, right?
yeah.
If the condition was winning, that would follow from those, right? Phoebe, did you have a question? Oh, okay. So then there's one more thing that's gonna come up on quick notes that I wanted to make a point about before quick notes. So how could I use the tree diagram if I were to ask what the probability is that I pull at least one red starburst while playing the game? How can I go about doing that?
adding, 12 out of 14.
Sorry?
12 over 14.
12 over, well, that was for this one. So regardless of if we win, what is the probability that just I play the game and I pull at least one red starburst while I play?
20 out of 30.
20 out of 30. Where did the 20 out of 30 come from?
From the 8 over 30.
Which 8 out of 30? This one?
Both of them, technically?
So, well, remember, so 12 out of 30 plus 8 out of 30. This is giving us our 20 divided by 30, right? But I said all I want to do is at least pull one red starburst, right?
4 over 6.
So, where-
4
so-
over 6.
how come 4 over 6?
Because what you
Oh,
wanted
is
is
it
to
just-
pull at least one red, so
Mhm.
overall, all of the sample space, it would.
Oh, so you got that from here, right? This was a
Yeah.
4 divided by 6?
Yeah.
But this is just the first one being red, right?
Is it just 12?
What about if the second one is red? Even if the first one is pink, I'm still at least pulling one red one, right?
Isn't it just 12 out of 30?
Well, 12 out of 30 is when both of them are
Yeah,
red, right?
but that's still considering that red was pulled in one
Right, so this is a possible, so this is what I was trying to get to. So you added these two, right?
of them.
You added these two because these are possible, in this case, are successes, right? Because this would be a success because at least one is red. This would be a success because at least one is red. But what else? Phoebe?
First one, the second one red, so you add a 2.
Exactly, right? So we would add another, because all we're looking for is any one of them being red.
Oh, is it okay to just subtract the yellow and yellow possibility from the overall?
Yeah, exactly. I was exactly going to say that in a second. So we look at all our branches that have at least one, right? So that's this branch, and also this branch, right? Because all we needed was, oh well, this one.
Getting at least one.
Right. But that's what I was going to say, which is where it comes up on quick notes, exactly what Raina had just said. If we take all our outcomes that don't have any red, right? What do we subtract that from, Raina? What did you say?
From 1.
From 1, right? Well, how come 1?
Because it always seems, sample space always seems to be 1.
Right.
Overall.
And we can't have any outcomes that have, other than the two outcomes of at least having one red and having no red ones, right? There's no other outcomes that exist, right? So those probabilities would have to be 1. We worked with that before. What did we say? We had a name for that, like, rule, right? What did we say that was?
I love.
I think I heard someone say it, but...
The complement?
Yeah, exactly. The complement, right? Because the complement of having at least one red one is having none, right? So, that is what we're going to write in a second. Okay. So, this is our quick notes. Remember, so our general multiplication rule comes from what we had before. So, we were saying before, what did we do in question 2 when they were independent? Hmm? Multiplied which one?
The same value?
Well, what does question 2
Each
say?
probability value, each
Right.
fraction.
The P of A times the P of B, right? That was when they were independent, right? But in this case, we were looking at dependent events, right? Was the probability of B the same anymore? No, right? We needed, our tree told us what? Our second probability that we were multiplying by in the tree diagram wasn't just the probability of B anymore, right? What was it?
It was minus the sample
right? So, well, when we had our tree, right, we had the probability of, for example, red. And this broke off to the probability that the second one was red, right? But it was the second one being red after what?
After what was taken out.
Given that the first one was red, right, Madeline? So given that the first one was red. This is what we multiplied, right?
Yeah.
So what should my general multiplication rule actually be? It's not just the probability of B anymore,
Is it being given?
it's B given A, exactly. Probability of B given that A already happened. Now the reason that this works in the general case, right? So this is for independent. So why was it that this, if this is the general case, how come this worked when they were independent? What did we just say? Right.
The values are
Charlie, yeah?
And that, that rule that's already been done right here.
Yeah, I mean, pretty much, right? But the reason that it works, right, is because we can replace these two. When they're independent, these two are equal. So that's what it is. So when it's independent, we know that P of B given A is the same as the probability of B no matter what, because the condition isn't changing our probability. But in the general case, this is what we need to know. This rule is going to work whether it is independent or dependent, right? So this is our probability of both things happening. The probability of A and B happening, right?
Oh, what did you write on the bottom independent is?
Oh, so for independent, we know that the probability of B given A
Got it.
is going to be equal to the probability of B regardless, right? So that's the connection there, is just that we were using this general multiplication rule before, we just didn't realize it, right? Because we were only looking at the standard probabilities without the condition, because the conditions were irrelevant, right? So everyone has this written down. So with the, in terms of the tree diagrams, what did we have? So we started with an event, right?
Right.
And we had that A could happen, right? Or what could I write here? So either A happens or A doesn't happen, right? So what could I write to represent that? Right? A, C, right? And how do I get to A? What did I use? Like,
Divide the probability of,
right. Not dividing though, we were just using the probability, right?
oh yeah, yeah.
So the probability of A happening lets us know when A is going to happen. So similarly, what can I use?
Probability of B
Well,
or A complement.
right.
Probability of not happening.
So the probability of A not happening, or the probability of A complement, is going to lead us to our event of A complement. Then we can break A up into two, right? So if after A happens, we can get to either some B or some C. What am I using to get from A to B? What did we just say before?
That A is happening.
Given A.
Exactly, Star. Raina, I think this is like kind of what you're saying too. And then, so what would I put here?
B given C. Or C given A.
C
Sorry.
given
And then this is A and B happening, right? So then this was the probability of A and B, right? And then here it would work the same way, right? So if A doesn't happen, but then B happens, what do I draw on this arrow?
Is it B given a complement?
Exactly, I drew it a little small here, but B given that A doesn't happen, right? And then, or C can happen, and then what would that one be?
What was that thing? C given the complement.
And then, yeah, these are all our four outcomes. So this is that A happens and C happens, This is that A doesn't happen and B happens. This is that A doesn't happen and C happens.
Isn't the, when we put it as a intersect form of that, not A not happening and plus B?
Right, so when we actually think about our probability, it would look like, yeah. So the complement of A intersection,
Isn't that equal to B minus A in the Venn diagram?
what do you mean, in which,
Like if we put this in the Venn diagram, would it be equal to B minus A?
oh, so if you're saying if we had a Venn diagram of two events happening,
Yeah, would it be B equal?
but remember, the events are dependent now, so we can't have a Venn diagram like this because we don't know what the sample of B is until we perform A,
Yeah,
right?
we only in the.
Right.
Mr. Ensign, can you explain what a complement is?
So a complement is just the opposite of A, right? So if, like in our other game, if we pulled a red one, what was the complement of pulling a red one? Exactly. It was whatever is not happening for A. And remember, we said that before, the reason that we use complements is because, what did we say about the probability of something happening and the probability of something not happening? Right?
Right.
Well, yeah. But does that make sense, Ian? Do you remember that?
Yes, thank you.
Okay. So is everyone like this diagram, just in the general sense, not in our example, but do these like notations make sense in terms of your diagram? Because the check your understanding, which is what we're going to work on for however much time we have left, I don't know, like 5 or 10 minutes. So there's a check your understanding on the bottom that has you construct your own tree diagram.
Go ahead and start the.
And you guys could get up and work at the vertical surfaces too. We're just going to spend the rest of class.
We only have 3 minutes.
Oh,
It would just
okay.
be tough to go vertical.
Yeah, I guess that's fair. So you guys could talk about it, get some ideas down.